Hello, my name is Joelle Midinger. I'm pleased to welcome you to this webinar. Today, I'll be talking about diffusing wave spectroscopy for microrheology measurements, with a particular focus on applications in food. LS Instruments is a Swiss company with seat in Fribourg, which was co-founded in 2010 by two professors, namely Frank Schaffeldt and Peter Schurtenberger, which are professors in colloidal and polymer physics and experts in light scattering. The outline of today's webinar is as follows. I will begin with an overview of the fundamentals, including a comparison of the two most prominent methods for rheological measurements. This will be followed by a more in-depth technical explanation of the DWS technology. In the second part, I will present a few real-life examples showcasing the use of DWS characterization in food applications. Let me start by comparing the most common methods used to extract the rheological properties of a sample: mechanical or bulk rheology and microrheology. In bulk rheology, an external force is applied to the sample, and the response of the entire material is measured at once. This gives us a macroscopic view of its behavior. In microrheology, passive to be precise, no external force is applied. Instead, the motion of nano or microparticles dispersed within the material is tracked to probe its response. There are different techniques for performing microrheology. The most common include video or particle tracking, dynamic light scattering, and diffusing wave spectroscopy. While video or particle tracking methods are well-established microscopic techniques, they have limitations. They are not very sensitive to small structural changes, making them suitable only for very soft materials with low modulus. Additionally, their frequency range is restricted by video frame rates, meaning they can only be used for low viscoelasticity materials. The same is true for DWS Microrheology, which is limited to very low viscoelastic materials due to a higher restricted frequency range. Then there is DWS, which offers a much broader frequency range, allowing us to study material behavior from low to higher viscoelasticity and at frequencies that are either difficult or impossible to access with bulk rheometry. That's why today I would like to introduce you to this still relatively unknown technology in more detail. Why would you choose microrheology as a complementary method to bulk rheology? Microrheology using diffusing wave spectroscopy is a non-contact method based on light scattering. This technique requires particles to be dispersed within the sample, which can either be naturally present, as in the case of emulsions, or intentionally added. The particles will experience their environment by Brownian diffusion through the sample. Their microscopic interaction with the environment determines their time-dependent displacement. This also means that you can probe the sample at rest, and no external force is applied to the sample, which is going to deform it. As a result, the technique is non-destructive and non-invasive, enabling repeated measurements on the same sample over time. Ideal for shelf life and stability testing, for example. Additionally, microrheology with DWS covers a broad frequency range, from 0.1 to over 1 million radians per second, in a single measurement that takes only seconds to a few minutes. Sample preparation, as it is a cuvette-based method, is straightforward, requiring only small volumes for analysis. Microrheology methods measure, as already mentioned, thermally driven motion of particles embedded within the sample over time. The analysis of this motion provides valuable insights into the microstructure, dynamics, and linear viscoelastic properties of soft materials and complex fluids, including colloids, foams, gels, and emulsions as found in cosmetics, dairy products, or special chemicals. Let's now take a closer look at the principle behind DWS technology, how it works, and what the resulting data looks like. So how does DWS work? Here is an animation illustrating the experimental setup. The sample in this case is either a transparent or translucent material to which we have added nanoparticles, or what we call tracer particles, or a sample that has naturally present particles dispersed in it. Light will be shone through the sample. The laser light will hit the dispersed tracer particles inside the sample. The photons of the incident light are scattered by the particles. This scattered light is going to be collected by the detector. As the particles move during the measurement time, the scattered light measured at the detector changes in intensity over time. This means we speak of a time-dependent measurement. The particles will move and their scattered intensity will hence fluctuate over time. The intensity fluctuations that are measured will be transformed into a correlation function from which a mean squared displacement is calculated. The mean squared displacement provides direct physical information about our sample. It shows how much the average particle moves in a given period of time. From the mean squared displacement curve, in short MSD curve, the microrheological parameters such as G' and G" and complex viscosity can be calculated. In the case of Newtonian behavior and known viscosity, in certain cases, even the average particle size can be measured. The position and shape of the mean squared displacement curve give a lot of insightful information about the sample's behavior and rheology. The fluctuations in intensity give information about how fast the particles are moving and also how far they can move. If the sample is Newtonian but highly viscous, the particles will move slowly, but their motion is not hindered. Faster intensity fluctuations are the result of faster particle motion, and a steeper slope is seen in the mean square displacement curve. Conversely, slower measured fluctuations relate to slower particle motion, and therefore a shallower slope with less displacement versus time is seen. In a Newtonian sample, it is only the particle size or the sample viscosity that affects the particle diffusion at the given temperature. You can use the technique to measure viscosity or particle size. In a viscoelastic sample, the particles might be able to move freely, but eventually their motion is stopped or hindered by the presence of the network. This is the kind of information with nanometer scale precision that will be measurable using DWS. In the case of a viscoelastic sample, the particle diffusion is hindered by the presence of a network in the sample. The particles will exert stress on the structure, and their absolute displacement, as measured by the MSD, is directly related to the elasticity of the network. More displacement resulting in a higher plateau would mean a lower modulus, while less displacement or a lower plateau would mean a higher modulus. From this, we can directly extract G' and G" with what is known as the modified Stokes-Einstein relation. In summary, what can the mean squared displacement tell us? A linear MSD is measured for purely viscous samples, as shown here in red, and the position of the curve is related only to the viscosity of the sample. If we see an inflection point, as is the case here in the green curve, and the slope of the MSD changes with a processing measurement, we are facing a viscoelastic sample with a weak microstructure. The particle motion is hindered and slowed down. The formation of a clear plateau, as is the case here in the blue curve, indicates the presence of a strong microstructure. The particle motion is completely stopped as they are confined within the network. With the technical groundwork in place, Let's take a closer look at some compelling real-life examples where DWS Microrheology played a key role in uncovering valuable information about the material behavior. I would like to start by showing you how to monitor a gelation process and detect the exact gelation temperature or gel point. Here you see the results of a very easy and natural system, gelatin. Tracer particles were added to the otherwise transparent sample to make it turbid. That's why the sample looks white. Gelatin is of course used as a food ingredient and is liquid at high temperatures, but is a gel at room temperature. To characterize the gelation temperature and monitor the gelation process, a temperature-dependent measurement was performed on the system. An automated measurement with temperature protocol was set by cooling the system from 50 degrees Celsius down to 15 degrees Celsius in steps of 5 degrees, but with smaller increment steps around the gelation point. Here, I show you the results in the form of the mean square displacement curves of the gelatin sample when cooled down from 50 to 15 degrees Celsius. At high temperatures, the MSD shows a slope of 1, indicating a liquid sample. Upon lowering the temperature, the slope changes. Especially the slopes at temperature 23 and 22 degrees show a clear change from a liquid state to a gel-like state. At 21 degrees, already a clear plateau shows, indicating an arrested sample. Using the instrument software to calculate G' and G" from this data, we can create the following plots. The red curve at 50 degrees shows that G" is proportional to the frequency that represents a liquid sample. At a temperature of 22.5 degrees Celsius, G' and G" are parallel, represented here in green, which is according to Larson and al. The rheological definition of a gel. With further decreasing temperature, the sample starts to show a constant G' at low frequency and an approximately linearly rising G" with frequency. A clear solid behavior is observed with G' above G" as shown here in blue. This corresponds to a gel and can be described by the Kelvin-Voigt model. The gelation temperature can also be confirmed by making a plot of G' versus temperature. The linear fit crosses the temperature axis exactly at 22.5 degrees Celsius, confirming once again that we have found the correct gelation temperature to be at 22.5 degrees. In this DWS example, I show you a study recently published by the Jiangsu Institute of Technology in collaboration with Penn State University. They explored how the pH influences the gelation kinetics of chitosan glutaraldehyde hydrogels utilizing both rotational rheometry and diffusing wave spectroscopy for analysis. They found that the non-invasive DWS technique offers a much more precise approach to monitor the microstructural evolution during the gelation process compared to the bulk rheometry. The external stresses applied in rotational rheometry disrupted the gelation process, which introduced artifacts, while DWS provided highly accurate gel point characterization. You can see here the G' and G" curves for the liquid sample before it forms a gel after 22 minutes. After the gelation, the gel continues to change during a stabilization step. This process was finished after 68 minutes. A common process that can be explored using DWS Microrheology is the production of yogurt. DWS can be applied to study in a non-invasive way the interaction of dairy proteins and the kinetics of aggregation in gelling systems under different destabilization conditions. Milk is naturally turbid and contains dispersed particles that can be used as tracer particles. The large aggregates of casein micelles with calcium phosphate clusters are among the most important constituents of milk for texturing. In the production process of yogurt or other food products such as cheese, this micellar system is perturbed by an external stimulus and a gelling process is started. It is highly important to control the coagulation reaction. Two reactions exist to destabilize milk: renetting and acidification. In this example, I would like to present the second, namely acidification. By the addition of lactic bacteria, the milk is fermented and the pH of the water phase is continuously reduced. The micellar stabilization is broken and the micelles undergo aggregation. This process has been studied by bulk rheology, but the method is too intrusive and not sensitive enough to study the fragile sol-gel transition. The mean square displacement is shown here at different pH values in the process of acidification. With DWS, you can see here the effect of the pH change becomes very apparent. We see that until a pH of 5.5, very little happens. But between pH 5.15 and pH 4.95, a very dramatic change in the mean square displacement occurs. Clearly, we can identify visually the gel point of acidifying milk at a pH of 4.9 with the help of the mean square displacement plots. This study was conducted in collaboration with Arla Foods as industrial partner, and we present the use of diffusing wave spectroscopy to monitor structural changes in aqueous whey-protein aggregate dispersions at temperatures up to 135 degrees Celsius. Different dispersions with varying salt concentrations were subjected to a controlled heating-cooling cycle to investigate temperature and salt-dependent structural evolution. All samples exhibited a decrease in viscosity with increasing temperature up to a transition temperature beyond which a shift toward more solid-like behavior was observed, which intensified with prolonged heating and upon cooling. This shows that DWS can be applied to characterize water-containing samples above their boiling point, and it can monitor structural changes during high-temperature processing and is hence able to provide new insights into the colloidal stability and interaction for industrial food processing applications. In this next example, I would like to show how the detection of formulation instabilities such as syneresis of phase separations can be easily and fastly conducted by DWS. These studies can be performed visually, but usually take a long time. Accelerated detection of instability can be performed using the DWS, as the method will detect changes in the microstructure at the moment of onset, and hence the time of detection can be highly reduced. With this study on a cosmetic formulation performed by Amin and colleagues, I would like to show how the visual test of usually 123 hours was reduced to only 3 hours using the DWS technology. Even though it is a cosmetic formulation, the principle is equally applicable to food emulsions. The onset of phase separation will affect the particle motion. In the emulsion I am showing here, no tracer particles were added. In the naturally turbid emulsion, the motion of the oil droplets was measured. Due to ongoing destabilization, the oil droplets were changing in size due to aggregation or coalescence. Larger particles diffuse slower in the same medium, which is visible in the mean square displacement. The shape and position of the mean square displacement plot are changing over time, clearly highlighting that the system is changing and larger particles are forming, identifiable as ongoing destabilization. In the case of a stable emulsion, surrounded here in green, no change in the mean square displacement could be seen. In the case of syneresis in a gel system, the particle motion will also be affected over time due to solvent expulsion. Either the particles become trapped in the denser gel phase that is forming, or they will move and stay in the liquid phase. In consequence, the change in particle diffusion can be easily followed in the mean square displacement plot. In the food industry, shelf life, mouthfeel, and flow properties are of utmost importance. These properties all result from interactions present between the system's constituents. The technology of DWS allows the measurement of samples in a sealed cuvette, avoiding solvent evaporation at any temperature and enabling easy shelf life tests. This format also facilitates simple automated sample exchange. Fragile systems can be studied without risk of destruction, as no external force will be applied to the system. The technique's sensitivity allows the detection of the smallest changes in the structure and the behavior of the system and is hence a well-suited technique to characterize processes such as gelation and possible instabilities in formulations. The technology also allows simple and fast rheological measurements over a large frequency and temperature range with fully automated measurements that can be programmed and executed with one single click. In the current times, the increased sophistication in the formulation of food and the design of food products demands faster and more accurate technologies to characterize the formulation's physical and chemical properties. It is of high importance to understand the balance and interaction between the food components during processing and storage. Diffusing wave spectroscopy offers significant potential in the food industry by being an advanced and complementary tool for the analysis of food texture, structure, and stability. By measuring the microscopic movements of particles in complex systems, DWS allows for a non-invasive and highly sensitive approach to monitor processes such as fermentation, gelation, and emulsification. Its ability to provide real-time insights into the behavior of food products at a microscopic level ensures faster and better quality control and supports accelerated innovation in food formulation. With these concluding remarks, I would like to thank you for your attention.